For example, titanium and vanadium in practice are passive to dilute non-oxidizing agents at room temperature. Titanium and vanadium are passive to H plus, even though 3D is highly reactive. Okay, it's because the actual rate is different. We know it's supposed to be reactive, but the actual rate is different. Then E naught values for Mn, Ni, and Zn are more negative than expected. For Mn, the reason is because Mn Zn, we know the reason because Zn2 plus is in D10, Mn2 plus is in D5. But for nickel, it is because of the high negative enthalpy of hydration. Then they have said that Mn2 plus and Mn3 plus and CO3 plus are strongest oxidizing agents in aqueous solutions. Ti2 plus, V2 plus, and Cr2 plus, they are strong reducing agents and will liberate hydrogen, such as this. E naught M1 M2 M2 M plus M2 plus 2 M values are not regular, can be explained from the irregular variations of ionization enthalpies, and it is given over here. Ionization enthalpy is delta H1 plus delta H2. That's your total ionization enthalpy for 2 plus. And also the sublimation enthalpy, which is relatively much less for your manganese and vanadium. Randomly by sublimation को लाके रखा है, but we have to know it. So yeah, so Cr2 plus is see, Fe2 plus is your D6. D6 is going to go to D5. Okay, D6 is going to go to D5. Fe2 plus D6 to D5 transition is happening. Cr2 plus 3D4 to 3D3 is happening transition. Now, which is more stable? Cr2 plus is better because you're getting a T2G. T2G is half filled. Okay. In E naught values, it is mostly seen. So, एक और बार बोल रहा हूँ, Cr2 plus Cr2 plus is a stronger reducing agent than Fe2 plus. Cr2 plus stronger reducing agent than Fe2 plus. T2G stability is more than half filled. Then the reason of complex formation of these d orbitals is because comparatively smaller size of metal ions, higher and ionic charges, availability of d orbitals for the bond formation. D orbital elements, d block elements also have a strong catalytic property because of they're based on multiple oxidation state. Catalyst has a solid surface involve the formation of bonds between reactant molecules and atoms on the surface of the catalyst. So yeah, it weakens the bonds, which in turn weakens the activation energy. So, anyways, guys, we have discussing the catalytic properties, right? So, Fe2 plus catalyzes to I minus to S2O8 2 minus to plus S2O minus to I2 minus I2 to SO4 2 minus. Right. So, how does it catalyze? Fe3 plus goes to Fe2 plus, and then Fe2 plus goes to Fe3 plus, and the corresponding reaction occurs. So, it's a very easy reaction. We can easily remember this. Formation of interstitial compounds, non-stoichiometric and neither typically nor ionic nor covalent. They have nothing basically. They are just weird. They are when small atoms are trapped in the crystal lattice of the metals. Okay, they have high melting points, higher than those of pure metals. Very hard. Some borides approach diamond hardness. Retain metallic conductivity and are chemically inert. Copper zinc alloy is brass. Copper tin alloy is bronze. Chromium, vanadium, tungsten, molybdenum, and manganese are used to produce a variety of steels and stainless steel. Ferrous alloys, basically. With these, they're alloyed, right? And they are homogeneous solid solutions. All right. So yeah. Um, this is fine. This is very chill. It's given to us that Cu2 plus is actually disproportionating to Cu2 plus Cu. All right. So yeah, that's it. I mean, Cu plus to Cu2 plus, even though electronically doesn't favor, it favors because Cu2 plus has high, what do you say, delta H hydration. Scandium oxides form MO oxides, which are covalent, and then apart from that, we have No higher oxide apart from Fe2O3 are known except for your FeO4 2 minus. All right. Mn2O7 is a covalent green colored oil. It's there in your NCRT exemplar. Number of oxidation number of metal increases, ionic character decreases. All right. Mn2O7 in particular is your covalent green oil. From here, we can also notice that um, V2O5 and Cr2O3 have low melting points. Acidic character is predominant in higher oxides. Mn2O7, which is a covalent green oil, gives HMNO4. CrO3 gives H2CrO4 and H2Cr2O7. V2O5 is amphoteric, all right, and it gives VO4 3 minus as well as VO2 plus salts. All right, so vanadium, there is gradual change from the basic V2O3 to less basic V2O5, V2O4, and amphoteric V2O5. V2O4 dissolves in acid to gives VO2 plus salts. V2O5 also reacts with alkalis as well as acids to give VO2 plus and VO4 3 minus. And CRO is a basic, but Cr2O3 is amphoteric. CRO is basic, Cr2O3 is amphoteric, V2O3 is basic, V2O4 is less basic, V2O5 is amphoteric, and Mn2O7 gets converted into HMNO4, and CrO3 gives H2CrO4 and H2Cr2O7. Then you have potassium dichromate, which is a super important reaction. First reaction is fusion of chromite ore, right? So basically, this is preparation of sodium chromate. So FeCr2O4 with Na2CO3, it gives your Na2CrO7 plus Fe2O3. All right, Fe2O3 is formed. Fe2 Na2CrO4 is your solution, and the insoluble part is Fe2O3. So FeCrO4 plus Na2CO3 gives Na2CrO4 and Fe2O3. Yellow solution of sodium chromate is filtered and acidified with sulfuric acid, which form orange sodium dichromate. All right, so we add into a H plus solution. It gives Na2CrO4, Cr2O7, Na2Cr2O7 in terms of acidic, and Na2Cr2O7.2H2 can be crystallized. So yeah, that's the flow of control. And yep, so flow control is iron chromate, Na2CO3, O2, all right, NO2CO3, O2. It gives sodium chromate, which is yellow. Then you add acidic medium, it gives sodium dichromate, which is more soluble than potassium dichromate. Then you add your KCl, and done. You have formed your K2Cr2O7. Orange crystal of potassium dichromate crystallize out. In acidic medium, Cr2O4 becomes your, what do you say, your boy. It becomes your boy. Bond angle of this is 126 degrees. Yeah. Sublimation enthalpy of, okay, this is all done, I think. Sorry. Where was I again? Yeah, here. No, after this. Yeah. Right here, I guess. So it says that CrO-Cr bond angle is 126 in acidic medium. CrO4 2 minus converts to Cr2O7, and it goes back in the respective backwards reaction. K2Cr2O7 in presence of H2O2 gives CrO5. It's blue butterfly in color. Amine alcohol in CrO5 shows blue color, which is your general knowledge question. These oxidation reactions we all know. Then potassium permanganate. Okay, MnO2 with 4 KOH gives K2MnO4. MnO4 2 minus gives in acidic medium gives MnO4 minus. So the process is first MnO2 with KOH and O2 gives K2MnO4. MnO2 with KOH plus O2 gives K2MnO4. K2MnO4, if you add an acidic medium, you get your respective MnO4 minus. Then alkaline oxidative fusion of MnO2, um, followed by electrolytic. Okay, basically. So fused with KOH or oxidized with air or KNO3, MnO2 forms MnO4 2 minus. Then MnO4 2 minus to MnO4 minus, you use electrolysis. That's all. In the laboratory, manganese 2 plus is oxidized by peroxide disulfate to permanganate. Potassium permanganate forms dark purple crystals which are isostructural to that of KClO4. Salt is not very soluble in water, but when it heated, it decomposes at 513 Kelvin. So KMnO4 gives K2MnO4 plus MnO2 plus O2. So all the reactions involving KMnO4 is MnO4. First we start with MnO2, right? MnO2. Then it becomes MnO4 2 minus, then MnO4 2 minus. So yeah, where was I? Then KMnO4 gives K2MnO4 and MnO2 and O2. Alright, and this is two physical properties of considerable interest: intense color and diamagnetism, along with temperature dependent weak paramagnetism. Um, okay, so yeah, that is just a fact based thing. Permanganate at H, concentration of H is equal to 1 should oxidize water, but in practice, the reaction is extremely slow unless either manganese 2 plus ions are present or the temperature is raised. So, yeah, then non GK formula is stuff that we don't know. Is this one. Manganese salt is oxidized to MnO2 in presence of zinc sulfate or zinc oxides, catalyzes the reaction. So MnO4 minus plus 3 Mn2 plus gives MnO2. Coming to F block elements, we have lanthanoid series. Atomic radii decreases from left to right. Okay, although it's not very regular, just like M3 plus given in the graph, it just properly decreases. So yeah, ZR and HF are separated difficultly. So yeah, basically here they've given C4 plus is favored by its noble gas configuration, but it's a strong oxidating agent reverting to the common 3 plus oxidation state. And it's given that it can also oxidize water, but the reaction rate is very slow, and therefore Ce4 plus is a good analytical reagent. This also reminds me of the fact that Ti and V are passive to H plus, even though 3D series is highly reactive to non-oxidizing dilute acids at room temperature. EU2 plus is F7, but even so, it'll want to revert to EU3 plus. It's a good reducing agent. So yeah, like that. Terbium with a 4 plus is a half-filled F orbital, but it's still an oxidate. Same way, samarium and europium is same. It exhibit both 2 and 3 oxidation state. So I'll be telling all the elements once. Lanthanum, cerium, praseodymium, neodymium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, ytterbium, thulium, ytterbium, and then lutetium. Note the trend: 4F7 5D1 6s2, 4F1 5D1 6s2. Cerium is an exception and gadolinium is an exception. 5D1 6s2, 4F1 5D1 6s2, 4F3 6s2, like that. All lanthanoids are silvery white soft metals and tarnish rapidly in air. Hardness increases, samarium being steel hard. Samarium is very hard and it has a high melting point. Samarium has the highest melting point. And yeah, density change smoothly except for europium and ytterbium and samarium and I think thulium. Okay. So we all know this. Ln releases H2 with acids. Halogens it forms LnH3. With H2 it forms LnOH thrice. With 2273 and carbon it forms Ln2, LnC2. Heated with N it forms Ln N. Heated with S it forms Ln2S and yeah, so on. So some extra points you should note down is CeOH thrice to LuOH thrice. Basic character is decreasing. Okay. CeOH thrice to LuOH thrice, Ce to Lu. Basic character is decreasing. Okay, basic character of the hydroxides are decreasing from left to right. Okay, and LNO, because due to high polarization, इसको भी मग up कर लो. Due to high polarization, LNOH thrice is less basic than a CaOH thrice, is more basic than AlOH thrice. So LNOH thrice more basic than CaOH twice, is is less basic than CaOH thrice, but it's more basic than AlOH thrice. Okay. Lanthanoids uses production of alloy steel for plates and pipes. Mish metal is a lanthanoid metal, um, 95%, 5% of iron and traces of this. Good deal of mish metal used in Mg based alloy to produce bullets, shell, and lighter flint. Mixed oxides of lanthanoids are employed as catalysts in petroleum cracking. Ln oxides, lanthanoid oxides, are used as phosphors in television screens and similar fluorescing surfaces. Now take a look at this question from your NCRT exemplar. Clearly, they can ask it. Are you scared? Yes, I am scared. Okay, I mean, we know now, right? Lanthanoid oxide, television screen. Alright, so lanthanoid, X ray screen, mish metal, lanthanoid metal plus iron. Okay, magnesium based alloy is bullet. Mixed oxide of Ln is used for petroleum cracking. Cracking. That's why NCRT exemplar is the best book I've seen for your JE mains. So first, lanthanoid oxide used for television screens, lanthanoid used for X-ray screen, mish metal used for lanthanoid. What do you say? Plus iron. Mish metal is lanthanoid plus iron. Mg based alloy is bullet. Mixed oxides of Ln used for petroleum cracking. So yeah, all of these are very important. Then we have configurations: actinium, thorium, protactinium, uranium, neptunium, plutonium, americum, curium, berkelium, californium, einsteinium, fermium, and mendelevium, nobelium, and last one is norentium. Exception occurs in protactinium, uranium, neptunium. Okay, exception. Here we have lanthanoid versus actinoid. Lanthanoids have less density than actinoids. Lanthanoid oxides and hydroxides are less basic. Actinoid oxides and hydroxides are more basic. They have less tendency of complex formation, lanthanoids. Actinoids have more tendency. So till neptunium and plutonium, the number of oxidation states keep increasing. Then from americum till lawrencium, it keeps decreasing. Common oxidation state is 3, but plutonium and neptunium can go up till 7. And 3 and 4 plus ions tend to hydrolyze. That's how it works. General characteristics and comparison with lanthanoids, though I've told you, but I'll still go through this. Highly reactive metals, finely divided, were very reactive. Boiling water on them gives a mixture of oxide and hydride. Combination with most nonmetal takes place at moderate temperatures. Hydrochloric acid attacks all metals, but most are slightly affected by nitric acid owing to the formation of protective oxide layers. Protective oxide layers are formed when your actinoids react with HNO3. Okay. Lanthanoids are more susceptibility of magnetism than actinoids.